Welcome to this talk that was previously given at Symposium on Computational Geometry 2019. My name is Amer Krivošija and I present the joint work with Alexander Munteanu. We are both at TU Dortmund. It is about probabilistic smallest enclosing ball problem in high dimensions, this time via subgradient sampling. Assume we want to place an antenna to serve clients, but in order to save energy, the radius of the enclosing ball has to be minimal. So, given n input points in d-dimensional Euclidean space R to the d, the smallest enclosing ball problem is to find a center C such that the maximum distance to the input is minimized. Now, we still want to place the antenna, but our clients can appear at various locations or even be not present. The input consists now of distributions of locations of points in R to the d, and the probabilistic smallest enclosing ball problem is to find a center C that minimizes the expected maximum distance to the input points realizations. We need to define the distance of a point, say C, and the non-empty finite subset P of R to the d. The distance is the maximum distance between C and the point P in P. Such defined distance M is a near metric on the set of non-empty finite subsets of R to the d. It can easily be modified to a proper metric. We state our problem formally. Given R, n discrete and independent distributions in D. The ith distribution is defined over Z locations that are either in R to the d or a bot symbol, which means that the point is not present. Point I is realized at location Qij with probability Pij. Then X is a random set drawn from D. The probabilistic smallest enclosing ball problem is to find the point C star that minimizes the expected distance to the realizations of X. The fastest known algorithm is fully polynomial time approximation scheme of Munteanu, Zola and Feldman, presented at SoCG 2014. It has this running time, basically linear in the input. The problem that we want to focus on is reducing the exponential dependence on the dimension of the space. We need first to solve the set median problem. Given finite family of big N non-empty sets, where each set contains at most small n number of points from R to the d, the problem is to find a center C such that the sum of the distances from C to the input sets is minimized. Here, blue, red, and green sets. This is a generalization of two famous problems. If there is only one set, then we have the smallest enclosing ball or one center problem. If each set is a singleton set, then we have one median problem. There are many algorithms based on a subgradient method for these two problems, as 1 plus epsilon approximations by Bedoyo and Clarkson for one center, and by Cohen and others for one median. The subgradient method is a simple one. We fix the step size and, starting from some point, iterate a fixed number of times in the direction opposite to a subgradient. How do we adapt this? First, to get control over approximation guarantee in reasonable running time, we need to pick a good starting point. If we sample set Pi at random, and take any point out of it, with reasonable probability the choice will be good. This means that within O of average cost to the optimal solution. Second, for the number of iterations, it suffices to run O of 1 over epsilon squared iterations. Third, to pick a good step size, we need an estimator for the average cost R. We adapt to our setting the work of Kumar, Sabharwal and Sen and get that 1 over epsilon samples of P suffice to approximate R. Fourth, the exact computation of subgradient in each of L steps needs time linear in big N, which is very expensive. But by sampling only one item in each iteration, we remove the dependence on big N. At last, it remains to find which point that we passed during running minimizes the goal function. Exact computation is again prohibitively expensive. Even to approximate f of c would cost the same. But we can find a point that 1 plus epsilon approximates the point that yields the optimum by adapting the sampling technique of Indyk and Torup. This technique is originally from the theory of discrete metric spaces. We state that for the input P, there is an algorithm based on the subgradient descent scheme presented on the previous slide that computes 1 plus epsilon approximation to the optimal solution of the set median problem with constant probability. This is its running time. After reading the input in time linear in small n, the size of the sets in P, is it possible to solve the set median problem on a summary sublinear in n, and simultaneously not exponential in D? Unfortunately, no. Using techniques of Agrawal and Charlotte Kumar, we showed that any data structure that would approximate maximum distance queries with better factor than roughly square root of 2 would require number of bits either linear in n or exponential in D. But on the positive side, there is a square root of 2 times 1 plus epsilon approximation algorithm that has sublinear time in n after reading of the input. If we replace the sets Pi by corsets of Badoyo and Clarkson and approximate maximum distances queries M using result of Goel, Indyk and Varadarajan. Munteanu and others showed that probabilistic smallest enclosing ball problem can be reduced to 2 deterministic instances of the set median problem. Now, big N is an exponential function of small n. We adapt their framework, but with following changes. Their sampling procedure had hidden dependency on D, which was considered a constant. In our case, the number of samples does not depend on D anymore. Sampled realizations are not sketched via corsets of exponential size. And we avoid the exhaustive grid search of exponential size. All that due to the set median solution. We state now that there is a 1 plus epsilon approximation algorithm for the probabilistic smallest enclosing ball problem with constant success probability. Its running time is now only linear in D. The support vector data description problem is equivalent to the smallest enclosing ball problem in big D-dimensional Hilbert space H. we are given positive semi-definite kernel function k and an associated feature mapping phi. The inner product in H, and thus the distances, is implicitly defined via kernel function, and it can be evaluated in time O of small d. The dimension big D of H, that can be much larger than small d, and even can be unbounded, for example in the case of the exponential kernel function. But now, by simulating our PSEB algorithm in H and computing the centers and the distances only implicitly, we get the first probabilistic extension of the SVDD problem. We state that there is a 1 plus epsilon approximation algorithm for probabilistic SVDD problem with time linear in D and N and polynomial in 1 over epsilon. The exponent is slightly larger than for the PSEB problem. To conclude, we have a 1 plus epsilon approximation algorithm for probabilistic smallest enclosing ball problem with time linear in dimension and no longer exponential. By simulating PSEB problem, and we got the first 1 plus epsilon approximation probabilistic support vector data description algorithm, which is a useful building block in machine learning. Finally, the dependency on small n cannot be sublinear in high dimensions unless losing a factor of roughly square root of 2. Thank you.